So we are moving on to chapter 17, which is the other half of unit 8, and it really just picks up right where chapter 16 left off. You can even see the title of the chapter. It's just additional aspects, like we're just moving on. It was a lot of information for just one chapter. So we're looking at basically the chemistry behind weak acids and how weak acids behave in solution. And we're going to learn in 17.1 about the common ion effect. We've already seen this when we looked at solutions where we were dissolving a solid, right? That if we dissolve solid silver iodide into a solution that already had iodide ions, the solubility decreased. So this is just the exact same idea, except now we're talking about a weak acid. So it basically says the extent of ionization of a weak electrolyte is decreased by adding the solution to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So weak electrolyte is a substance that is ionic. That's what the electrolyte part means, that it will conduct electricity when in solution, but weak means it doesn't fully dissociate. And basically all that's saying is that you can see that here's the acetate ion. So a strong electrolyte would be something like sodium acetate or potassium acetate, something that dissociated completely. And when I add that to a solution of acetic acid, it will push the equilibrium to the left-hand side, making more of the acetic acid with the hydrogen. And what that will do is that will decrease the H3O plus. And then if we decrease the H3O plus, what happens to the pH of the solution? And this is tricky. You have to really, condition your mind to remember this, that if it's less acidic, it has a higher pH. So the pH actually increases in this scenario. Okay? So then the question here is, okay, so how much? Like this is actually now quantify it rather than just looking at it from a Le Chatelier's principle standpoint. So what is the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution? So we know that anytime the question is asking what is the pH, that means I'm going to need to know the concentration of the H3O plus at equilibrium. And we can find those on an ice chart. And we start by writing the balanced chemical equation. And again, if you don't want to write out all of acetic acid, you can just write, a weak acid plus water, and that will react to make H3O plus and the acetate ion or the conjugate base A minus. So remember we started with 0.3 moles of this and 0.3 moles of this, and water we don't even count, and we start out with none of that. And then of course this guy will go down by some amount, these two will go up by some amount, and then we can remember that if we're talking about weak acids and weak bases, this number right here can be negligible. We don't need to worry about how much it actually goes down, because we know that acetic acid is a weak acid, and in comparison with how many moles we already have, it's not going to make a difference to one or two significant figures. So this is just going to stay 0.30, and this will stay at 0.30. And then, we have our Ka formula. Ka is the concentration of the H3O plus times the concentration of the A minus over the concentration of that weak acid. And plug in our numbers. 1.8 times 10 to the negative 5 is the Ka for acetic acid. This would be 0.30 times X over 0.30. Well, that's easy. So X, and I always say, what is that equal to? It's equal to the concentration of the H3O plus, in this case, is 1.8 times 10 to the negative 5. And we talked about this a little bit last chapter. How can I estimate what the pH will be, right? And the pH is always going to be one number less than the exponent. So the pH is going to be 4 point something. And we plug that into our calculator, and it's 4.74. Okay? So that is the pH of a weak acid when you have the common ion effect taking place. Here is another question. And it's just asking which of the following statements is true. The equilibrium constant for the reaction changes as pH changes. We know that's not true. Hopefully we know that what changes the equilibrium constant, the only thing that can change the equilibrium constant is the temperature. If you add the soluble Ka to a solution of HA that is at equilibrium, the concentration of HA would decrease. Well, what we've seen is that if we add that common ion effect, it pushes the equilibrium to the left, which would mean that the concentration of HA would actually increase. If you add a soluble salt to the solution at equilibrium, the concentration of A- would decrease. Well, no, we would see that it would push the equilibrium that way, but remember, I'm just going to go back, right? Negligible. Like it may decrease, but not to a very big extent. If you add the soluble salt Ka to a solution of HA that is at equilibrium, the pH would increase. That was the exact scenario that we saw. Okay, here's another mathematical question with this. Calculate the fluoride ion concentration. So now this is, right, basically the conjugate base. And pH of a solution that is 0.2 molar in HF and 0.1 molar in HCl. So what do we need to calculate pH? Well, we know pH is the negative log of the concentration of H+. And we can find those in a ice chart. So let's start our ice chart here. It is HF plus H2O in equilibrium with H3O plus F minus. Okay, what is the initial? So our HF is 0.20. We don't care about water. The initial acid concentration. Remember, this didn't say we started out with any F minus. That's what the question is asking us is what is the fluoride ion concentration in this? So the acid concentration, this H3O plus, this is really the concentration of the H plus or, right, HCl. It tells us that there's 0.1 moles of HCl, which means, and we know HCl is a strong acid, it will fully dissociate. So this is going to be 0.10 and this is 0. Same as usual. And again, it's a weak acid, so the X's are going to be negligible unless they're compared with 0. So this would be 0.20, this would be 0.10, and this would be X. Okay, so 6.8 times 10 to the negative 4, that's the Ka of hydrofluoric acid, is equal to 0.10 times X over 0.20. So we solve for X. X is equal to, of course, the concentration of the fluoride ion, and that equals 0.00136 molarity, or maybe to two significant figures, 0.0014 molarity. That's the concentration of the F minus. The question also asked us to find the pH of the solution. Well, the pH of the solution we know would be the negative log of the H3O plus concentration, and we actually really didn't even need to do any additional problems to do that because we know that this is 0.1. So the negative log of 0.10, of course, will be just 1. So the pH will be 1. The pH really wasn't affected by the amount that the HF actually dissociated because the HF, being a weak acid anyways, dissociates very little. And then in comparison with how much H3O plus there already was, it really made no difference, especially when looking at that pH.